So the situation that we are talking about is probably like this. There is one ball, there is maybe another ball. I can keep them in contact in any way, it doesn't matter. So there will always be a common normal at this point, which will go through the center of the first ball and the center of the second ball. So the common normal is going to be a diameter for both of these balls, and however I distort the view, I can always find a view where I can keep the balls like this and say that the common normal is this red colored line. This is the common normal. So this is probably the n-axis. And then there is a perpendicular axis here, which is going to be the t-axis. So let's take that t-axis too. Yeah. So let's say this axis is the so-called t-axis. And these two balls, because the center of mass of the first ball lies on the line of impact and the center of mass of the second ball also lies on the line of impact, this is a central collision. But then, because the velocities of these balls have not yet been assumed, I will assume them such that they are not along this line. It will be an oblique collision. Let us say that this ball is A and that the other one is B. And let's say that this ball A has got a velocity that is along some line, somewhere, we have no clue. So let's just assume some direction randomly. Let us say this is how the velocity of this ball A was oriented. So this is UA, and let's say there is UB. So this ball B was also moving in a certain way. Let me also change probably the color of this ball here and that of its center and this point here. So let's say the velocity of this ball B is like that at the moment of collision, and then they hit each other, and this is what happens before. And after the collision, what happens is that their velocities will undergo a change. So if I just copy this, maybe I can make it smaller too, yeah, and paste it here. Yeah, okay. Now there is a force on ball A along this line of impact, so that force will be leftwards. So I'm expecting that there will be a change in momentum of this ball in the leftward direction, and so the final velocity of A will be shifting somewhere to this side. So maybe ball A moves in a certain different way, like probably this. This is VA, and there is a force on ball B towards the right hand side. So I expect that this ball B will suffer a change in its momentum along the n-axis, and this final velocity will be shifting towards this side somewhere. So maybe I'll just take this one and say that this is how the velocity of B is finally. So this is VB. So I've got UA, and then I've got UB here, and then I've got VA and VB. And what are the equations that I can write? So again, the assumption here is that I've got smooth spherical objects. So because I've got smooth balls, there is no force of friction between them. So there is no force on either of these balls along the tangential axis. If there is no force along the tangential axis, then their momentas along the tangential axis will undergo no change. And I can say that the velocity of A, so since F force on A along the tangential axis is 0 and force on B along the tangential axis is also 0, therefore velocity of A along the tangential axis before the collision, so that's why I've used U, is equal to the velocity of A along the tangential axis after the collision. So I'm using a V here. And I can also say that the velocity of B along the tangential axis, so U, initial velocity of B along the tangential axis, is equal to the final velocity of B along the tangential axis. So these are two equations that I've got. What else? I can conserve the momentum along this n-axis as long as I treat these two balls as one system, because then their force of interaction becomes an internal force of the system. So along the n-axis, So let me say here, for the system of balls A plus B along the n-axis, you can say that mass of A times the initial velocity of A along the normal axis plus mass of B times the initial velocity of B along the normal axis is equal to mass of A times final velocity of A along the normal axis plus mass of B times the final velocity of B along the normal axis. So this is the total initial momentum of system. This is the total final momentum of the system along the normal axis, and that should be conserved. So I've got a third equation. So I've got one equation, I've got two equations, here I've got a third equation, and then I should be able to write an equation for the coefficient of restitution also. So there is an E equation also. And so you have to keep in mind that the equation for E will always be written only along the line of impact. So here I have to write the equation for E along the normal axis only, and the way in which I have shown you the velocities, I will have to write something like E is equal to the speed of separation. So at what speed are they going to separate along the normal axis? So maybe I will have to rotate this in the other directions. So I will take this vector and I will just rotate it somewhere there. Maybe due to the collision it just happened to go in that direction, and maybe due to the collision this green ball happened to go in that direction. So when I find out the component of VB along the normal axis, it will be to the right, and the component of VA along the normal axis, it will be towards the left. And if I find out the total speed of separation, it will be this component plus that component. So it will be the VB normal component plus VA normal component divided by, and the speed of approach. Again, the speed of approach will be UA's normal component here and UB's normal component here, and because of both of these there will be an approach. So U of B along the normal axis plus U of A along the normal axis, where I should actually have used a minus sign if I was trying to write this equation in terms of vectors, but what I've done is I have already done that. So after using the minus signs and everything, I will end up with just these numbers. So here these are not vectors anymore, these are only numbers. So in fact I can also put a mod if you wish, but then I think it is fairly well understood that these are only numbers. So this is how I can write an equation for E along the normal axis, and this equation is the fourth equation that is going to help me solve things. Now this is a fairly general approach, but there is also one very interesting specific result. So let's go for that specific case. Let's say, so let's say there is a specific case of this oblique central collision where ball B is stationary before the collision, so this is the first assumption. The second assumption is that it's an elastic collision, perfectly elastic collision. Which means that E is 1. And third and last is that these two balls A and B have equal mass, or they are identical. Let us say balls A and B have equal mass. So these are the assumptions, and how can we draw this particular situation? So let's say there is this diagram that I want to take advantage of, and there is B stationary and A moving to the right hand side, but A is not quite there. So A should probably be shown coming and hitting B like this. Yeah. Yeah. Yes. So this ball A was coming from the left hand side there and moving towards the right hand side. So it has got an initial velocity UA towards the right, and its mass is MA. And of course we are saying that the masses are equal, so I will eventually say that MA is equal to MB. We will do that, but for now this is MA, this ball is MB, and its initial velocity is 0. And I know that there will be an impact between these two balls, and there will be forces acting at this particular place where they are in contact, and there will be a common normal. That common normal will be called the line of impact, and the forces will be along the line of impact. And since B was initially stationary and the only force that acts on B is along that particular direction, after the collision B will definitely start moving in that particular direction. So I can say that B starts moving this way. That is essentially how the line of impact will look like, right? So if I produce this backwards, it will go through this point and then like that. So let me call this angle as beta. And this ball A after the collision will start probably moving in some direction there, such that its velocity will make an angle alpha with the horizontal. So this is the line of impact. Let me just produce the line of impact like this. Yeah. So good enough. This is the line of impact, and this is the situation before the collision. And what is going to happen after the collision? Yeah, here. So the situation after the collision is as it looks on the right hand side, where I have got this object B moving with a velocity VB. So it moves with a velocity VB here, and this guy has a velocity VA finally in some direction there. And the angle that this velocity VA makes with the horizontal is alpha, right? And I know that here this angle is beta, so I can probably produce this back, make it go through that center again, and show you where that angle beta is here. That angle beta is the one marked in red, right? So I've got this, and what equations can I write? So the equations that I can write now are, first let me try to write one equation for the normal axis. So for n axis, and in fact this is not the n axis anymore, so let me remove that notation. Yeah, right. So I hope you have understood that change, because what was happening here was that the two balls were hitting each other like this, and the normal axis was in fact the x-axis also. But here, because the balls are hitting each other in a different way, this green axis which I've drawn here is the normal axis. So this axis is not the normal axis anymore. This is the x-axis, and this will then become the y-axis. This is the normal axis, and the perpendicular axis here will become the t-axis. So I'm going to show you how to write equations for x and y axis here. So for the x-axis, you will have MAUA is equal to MB UB cos beta plus MA, not UB, this is VB, so sorry, VB cos beta plus MA VA cos alpha. This is probably equation number 1. And for the y-axis, so initially there was no momentum along the y-axis for the system of two balls. So finally also there should be no momentum along the y-axis. So the momentum of A along plus y-axis should exactly be equal to the momentum of B along the negative y-axis. So the two momentas must be equal and opposite. So I have got MA VA sine alpha along the plus y is equal to MB VB sine beta along the negative y. So I have got for y-axis MA VA sine alpha is equal to MB VB sine beta. Now this I can write in a slightly different form, and I can say 0 is equal to minus MA VA sine alpha plus MB VB sine beta. So I've got this. This is probably equation number 2. And I can have a third equation also, that's for the coefficient of restitution. That should be used only for the normal axis. So let us also try to write the equation for E along the normal axis. What is that equation which I have? So along the normal axis, the speed of separation is, so I should go to this final figure. That it is what happens exactly after the collision. So VB is the speed at which B moves along that line, and VA cos of alpha plus beta is the speed at which A moves along that green line. So I've got E is equal to VB minus VA cos of alpha plus beta, and the speed of approach. So let me go to whatever happens before the collision, and A approaches B along this green line with a speed of UA cos beta. So here I should have UA cos beta, and this will give me EUA cos beta is equal to I can say VB minus VA cos of alpha plus beta, and this is probably equation number 3. So this format here, you see I've got a cos of alpha plus beta, gives me an idea of how to solve this, because I know that cos of alpha plus beta is cos alpha cos beta minus sine alpha sine beta. So I have already got cos beta here, and I have already got sine alpha here. So perhaps if I multiply this entire expression by cos alpha and this entire expression by perhaps sine beta, and then try to solve, now I will end up with cos of alpha plus beta. So what do I get? So I say that let's multiply equation number 1 by cos alpha plus equation number 2 by, and where is equation number 2? Here, by sine beta. Sine beta. I want to take advantage of this term, sorry, MA VA cos alpha and MA VA sine alpha. So here if I have cos beta, here if I have sine beta, I think the job will be done. So that is why I have cos alpha there, not cos alpha, cos beta. I should multiply one by cos beta and second by sine beta. Yeah. Now the job will be done. So sine beta, and what do I end up with? So it gives me, gives on the left hand side MA UA cos beta, MA UA cos beta, and here on the left hand side I won't have anything. So this is the total left hand side, and all that is equal to, when I use cos beta here, I will get a cos squared beta, and when I use a sine beta with the second one, I'm going to get a sine squared beta. So here I have got a cos squared beta after multiplying throughout by cos beta, and here after multiplying throughout by sine beta, I've got a sine squared beta. And when I add up these two equations, their right hand sides will have mb vb cos squared beta and mb vb sin squared beta. So it will give me just mb into vb. mb into vb. Then the next term, so ma va cos alpha cos beta and minus ma va sin alpha sin beta. So I'm going to get minus ma va cos of alpha plus beta. This is what I will get after I manipulate equations 1 and 2 like this. Divide throughout by ma. So you are going to get ua cos beta is equal to mb by ma into vb minus va cos of alpha plus beta. This is probably equation number 4. I can call it 4. And once I have 4, what do? I see that 4 and 3 have some kind of resemblance, and E is the only thing that is not the same on the left hand side. The structure of right hand side is also pretty similar. So that's where these assumptions will come into play. You see, I have assumed it to be a perfectly elastic collision, so E becomes 1. So when E becomes 1, the LHSs are exactly equal. And when I assume that the two masses are exactly equal, balls A and B have equal masses, then you will see that this ratio mb by ma will also become 1. Right. So what do we have got? I think I'll get a plus here. Yeah, I will get a plus here. I have made that mistake because there will be MAVA cos alpha cos beta and minus MAVA sin alpha sin beta. So MAVA taken out, cos alpha cos beta minus sin alpha sin beta, that will give me plus MAVA cos of alpha plus beta. So I'll end up with a plus here. So I see that these two terms will be exactly equal if E is 1, and the first term will also be equal if MB by MA is 1, so equal masses, but there is a minus here and there's a plus here. So what I can do is I can say that these two terms must actually be 0. Otherwise there is no way that 3 and 4 can be true simultaneously. Or maybe you can just subtract if you just want to do it, so you can do a 4 minus a 3. So the LHS will become 0, the RHS, the first term will become a 0, and the second term will give you 2 times of VA cos alpha plus beta, and so that should be equal to 0. So either ways you will get VA cos of alpha plus beta is equal to 0 if E is 1 and MB is equal to MA. And this equation says that alpha plus beta should be equal to 90 degrees. So it's a very specific result, but useful in certain problems. So you should keep it in mind that for oblique elastic collision of two equal masses, so in case of oblique elastic collision of two equal masses, the masses or two spherical balls will move perpendicular to each other, will move along perpendicular lines, will move along lines perpendicular to each other after the collision. So keep in mind this particular result.